Good morning, everyone, and welcome to this lecture. This is lecture number 1, and we are dealing with magnetic effects of current. Now, as soon as we talk about magnetic effect, we must just see what is a magnet and what does a magnet do. What is a magnet and what does a magnet do? Yes? What is a magnet? And what does a magnet do? No idea? Okay. Have you heard the term magnet? Oh,
Yes,
no.
sir.
Okay, so a magnet attracts magnetic substances. Magnetic substance like iron, cobalt, nickel. When a magnet is freely suspended from a ceiling with a thread, it will always rest in the north-south direction. A magnet has two poles, north and the south. Like poles repel each other, and unlike poles attract each other. I hope we know these things
Yes.
about a magnet. Now, what we are going to understand here is the concept of a bar magnet. What do you mean by a bar magnet? What do you mean by a bar magnet? Yes, never heard this term? Bar magnet?
A magnet which is in the shape of a cuboid.
A magnet which is in the shape of a bar, a chocolate bar. You can call that as a bar magnet. Name comes from the chocolate thing. A bar magnet. A bar magnet is a magnet in which this north and south pole of the magnet are at a very small distance from each other. Now every bar magnet has a north and a south pole, and you can see this north and the south pole are not exactly at the ends. They are slightly they are slightly they are slightly inside of these poles. This length is known as the magnetic length. Magnetic length. And this ratio of magnetic length and the end-to-end distance is 5/6. Do you see this? The poles do not exactly lie
Yes.
at the corners, at the edges, slightly inside. Here it is given as, it is called as effective length. You can also call it magnetic length Lm, and the other length is known as the geometric length, the distance from the one end of the magnet to the other end of the magnet. You can call it as the geometric. You may call it as the geometric length. Do we understand this?
Yes.
We have already seen the properties of a magnet. Here I will just again show it to you with diagram. If a magnet is suspended freely, it will always rest in the north-south direction. Why does this happen? Because your earth is also a magnet, and the magnetic field of earth causes this magnet, freely suspended magnet, to rest in the north-south direction. Do we understand this?
Yes, sir.
If we have a magnet has two poles. If I cut a magnet into two halves, I will not get a single north pole and single south pole. So we see that poles always exist in pair. Magnetic poles always exist in pair. Magnetic monopoles do not exist. Do we understand this?
Yes.
Electric monopoles exist. You can have a positive charge, isolated positive charge. You can also have an isolated negative charge. But you cannot have an isolated north pole. You cannot have an isolated south pole. Do we understand this?
Yes.
And remember, there is one saying that repulsion is a sure shot test of magnetism. Do you know this? If two bodies are repelling, then they might be charged or they might have magnetic properties. Repulsion is always a sure shot test of magnetism or having charge. We have discussed this in the electrostatics wala chapter. Yes or no?
Yes.
So these are the properties that you must remember. I'll give you 2 minutes to note it down fast. Okay, then we move on to the next concept, and the next thing that we have to understand is the pole strength of a magnet. Now, what do you mean by pole strength of the magnet? A magnet is going to attract other magnets and magnetic material. The strength with which it attracts other materials or other magnets is known as its pole strength. The pole strength of a magnet. The pole strength of a magnet is the ability for this magnet to attract other magnets or magnetic substances. This is represented by the small letter M, as you can see this. Now, this north pole is given the designation as the positive pole, or it is said to be having a pole strength of plus M. The negative pole strength is given to south pole, but that does not mean that the north pole is having more strength and south pole is having less strength. This is just plus and minus given just to differentiate that they are different. Do we understand this?
Yes.
Now this magnetic pole strength M, what type of quantity it is? Remember this units, its dimension, because they are coming in exam these days, especially in the topic of dimension analysis. It is a scalar quantity. The pole strength of north and south are plus M and minus M. The SI unit is ampere into meter or Newton per Tesla. And the dimensions are LA. L means length, meter. A means current, ampere. Do we understand this? Do we understand this?
Yes, sir.
Now this magnetic pole strength of a magnet, and this is a very important point, it depends on the type of the material and its cross-sectional area. The magnetic pole strength does not depend on the length of the magnet. The magnetic pole strength of a magnet does not depend on its length. It only depends on the material with which the magnet is made. And so magnetic pole strength depends on the material and it depends on the area of cross section. Magnetic pole strength does not depend on the length of the magnet. This is a very important thing that you must remember. The magnetic pole strength. I'll give you 2 minutes to note it down. Now, whenever you talk about any magnet, in order to understand what this magnet is, we do not define the magnet in terms of its pole strength. We always try to define a magnet, its magnetic properties, in terms of a vector which is known as a magnetic dipole moment. This magnetic dipole moment, M vector, it tells us about how powerful that magnet is. We don't define the magnet in terms of the pole strength, define the magnet in terms of the magnetic dipole moment, M vector. And this M vector is equal to M into 2L vector, where M is the magnetic pole strength and 2L is actually the magnetic length of the magnet. That means it is the length, it is the effective length or the magnetic length of the magnet. It's the distance between the two poles. Do we understand this?
Yes.
This magnetic moment or magnetic dipole moment is a vector quantity and it is always directed from where to where? It is directed from south to north. Do we understand this?
Yes.
The SI unit of this magnetic dipole moment is ampere meter square. L is AL square. I'll give you 2 minutes to note this down. Everyone understands this?
Yes, sir.
Now we can also see and remember the magnetic moments of various type of bodies. We will again come across these terms when we go into the topic further, but we can, if we can understand it here, it will be better. A current carrying coil, a current carrying coil will create magnetic field. A current carrying wire is going to create magnetic field. So a current carrying coil will have a magnetic field, will create a magnetic field, and we can treat it as a magnet. If we can treat a current carrying coil as a magnet, then the magnetic dipole moment of this magnet is given by I into A, or N I into A, where N is the number of turn, I is the current, and A is the area vector. Do you remember that area vector of a body? Yes or no?
Yes, sir.
So you can write the magnetic moment of a current carrying coil as Ni into the direction of area vector. And how do you find the direction of area vector? You turn your fingers in the direction of current. The direction of thumb gives you the direction of the area vector, which is also the direction of magnetic dipole moment. Also, wherever your thumb is pointing, that means it is your north pole. So for the north pole of this magnet would be here and south pole will be here. For this magnet, north pole is here and south pole is here. Do we understand this?
Yes, sir.
Similarly, if a electron or a charged particle is moving in a circular path, let me draw it here. If a charged particle is moving in a circular path, this is a charged particle. It is moving in a circular path of radius r. If the charge of this particle is q and it is moving with a velocity v or an angular velocity omega, you can also treat this as a current carrying wire. Current in this wire will be equal to q divided by t. Do we remember this? Yes or no?
Yes, sir.
So if you know the current, you can find out the magnetic moment by multiplying current with the number of turns. Your number of turns will be 1 multiplied by the area. If you do it, these are the formulas that you will get. You can find this magnetic moment as E, the charge of the electron, if it is an electron, into V into area vector, or you can find it out from different ways. This L is the angular momentum, and we will see that you can find out if the body is a solid body. You can find the magnetic moment of that solid body by multiplying it, by multiplying E by 2m or charge by 2m multiplied by the angular momentum. Angular momentum. Do we understand this formula?
Yes, sir.
I'll give you 2 minutes to note it down.
Done.
Now, if you have rotating bodies, let us say for an example, you have a rod, rod of mass m and length L rotating with an angular velocity omega, and the charge on this rod is Q. This rod can also be treated as a magnet. Remember, the magnetic dipole moment of this rod can be written as Q by 2m multiplied by L. What is this L?
Angular momentum.
Q by 2m multiplied by I omega. And how much is the I of this rod? About the end? Obviously, you have forgotten. ml square by 3 into omega. In fact, I can write it as a vector thing. So you also know the magnitude and you also know the direction. So this is the formula for magnetic moment of a rotating body in terms of its angular momentum. You can note down this formula, and this formula would be used wherever you have a rotating body like this. Then remember, this magnetic dipole moment is a vector quantity. So if you have two magnets at different orientations, if you combine these two magnets, the combined magnetic moment will be given by the vector addition. As you can see here, the magnetic dipole moment of this magnet is going like this, and the magnetic dipole moment of this magnet is going like this. The net magnetic dipole moment will be like this. So these are two vectors. We have to add the two vectors. Do we understand this? A square plus b square plus 2ab cos theta. We understand this?
Yes, sir.
Similar is the case with this one, similar is the case with this one, and similar is the case with this one. We have just seen the angle between the two bar magnets, the angle between the magnetic dipole moment of the two bar magnets, and then we use vector addition to find out the net magnetic dipole moment. Do we understand this?
Yes, sir.
Note this down. Any of this can come as a question in your exam. Okay, sometimes you might come across this term which is known as the Bohr magnetron. Don't get confused by this term. This Bohr magnetron is nothing but the magnetic dipole moment of an electron in the innermost orbit of hydrogen atom. EH by 4 pi m, we will come across this in modern physics. So we just remember this Bohr magnetron. The next thing is magnetic dipole moment of a current carrying wire. Current carrying wire does not have an area. If it is a straight wire, it does not have any area. The magnetic dipole moment is zero. Do we understand this?
Yes, sir.
Similarly, magnetic dipole moment of a toroid is zero. What is a toroid? You might have seen a solenoid. Do you see? Do you know a solenoid? Solenoid is straight, and you
Yes,
have
sir.
wire around it. Yes or no? Do we understand solenoid? Solenoid.
Yes, sir.
If I turn this solenoid into a circular thing, just like the tube of a cycle tire or tube of a car tire. These days car tires do not have tube, but if you imagine the tube of a tire and you wind a wire on that tube, that becomes a toroid. The magnetic dipole moment of a toroid is also zero. Do we understand this?
Yes, sir.
And this magnetic dipole moment depends on the length. So if you decrease the length, if you move it in any particular shape, the magnetic dipole moment will change. In first case, the magnetic dipole moment is m into L. In second case, it is m into L by root 2. Do we understand this? Because the length, the distance between the two poles have changed. Are you getting my point?
Yes, sir.
These are very important concepts that I'm giving you. Note them down very peculiarly. Any question can come from here. These are some of the common questions that I've seen come in exams. You have a bar magnet. As you can see in first case, the magnetic pole strength is small m and the magnetic dipole moment is capital M. Now, the question that comes is they cut it into different ways. They cut it along this line. If they cut it along this line, the magnetic pole strength, because the area becomes half. Do you understand this? Yes or no?
Yes, sir.
The magnetic pole strength becomes half. The length remains same, so the magnetic dipole moment becomes half. Do we understand what I am saying here?
Yes, sir.
If I break it up like this, the magnetic pole strength remains same, but since the length becomes half, therefore the magnetic dipole becomes half. First listen to me, then I'll give you time to write, don't worry. Do you understand this?
Yes.
Now, if you have a bigger bar magnet like this, and you break it up into small parts, the length of the bar magnet is L, the breadth of the bar magnet is B. Then you can see one such part will have a length equal to L by root over N, yes or no?
Yes.
We understand this, everyone? The breadth of each part will be B divided by root over N. Basically, what I am doing is I am cutting this bar magnet into smaller portions. Do we understand this?
Yes, sir.
And we can find out the magnetic dipole moment of any smaller part. For example, if I cut a bar magnet into 4 parts, 2 parts like this and 2 parts like this, we can get the value like this. If they are cut into n equal divisions, do we understand this? N equal parts.
Yes, sir.
So note this down. I'll give you 2 minutes to do it. Now what we have seen up till now is magnet and magnetic dipole moment. Then we can see a electric dipole and electric dipole moment, and it is exactly similar to what we had seen. Electric dipole will consist of what? It will consist of a positive charge and a negative charge. Yes or no?
Yes, sir.
Separated by a very small distance, let us say 2L. This 2L is known as the length of the dipole or the dipole axis. Do we understand this?
Yes, sir.
This 2L, so you can just write it fast. This 2L, this 2L vector, this 2L is a vector. This is known as the dipole axis. Dipole axis. And it is directed from where to where? It is directed from negative charge towards the positive charge. Do we understand this?
Yes, sir.
Every dipole, electric dipole will have electric dipole moment. This P will be equal to electric dipole moment, and this P vector will be equal to Q multiplied by 2L vector. Do we understand this?
Yes, sir.
The what type of quantity will be electric dipole moment? Electric dipole moment will be a vector quantity. Do we understand this?
Yes, sir.
The SI unit would be coulomb meter and the dimension will be ALT. Do we understand this?
Yes, sir.
Everyone understands this? So whatever we are going to do for electric dipole or whatever we are going to do for magnetic dipole, they both are similar things. Exactly similar, in fact. The only difference is for electric dipole, we have electric dipole moment P vector, which is given as Q into 2L vector. For magnetic dipole, we have magnetic dipole moment M vector, which is M into 2L vectors. Give you 2 minutes to note this down. Then the next thing is magnetic field. It is the space around a magnet or a current carrying wire where magnetic effects of that wire or the current or that magnet can be felt. Do we understand this? Yes or no? Yes or no?
Yes, sir.
It's the region around a magnet where you can experience magnetic effects or magnetic force, and it is expressed by the strength of the magnetic field. It is similar to strength of the electric field denoted by the letter B vector. It is a vector quantity. Do we understand this?
Yes, sir.
Everyone understands this.
Yes, sir.
Now, if you talk about this magnetic field, this magnetic field is expressed in terms of magnetic field lines. Do we understand this?
Yes, sir.
Or magnetic lines of force. And these magnetic lines of force are going from where to where? Outside the magnet, they are going from,
North to south.
and inside the magnet, they are going from.
South to north.
Do we understand this?
Yes, sir.
Everyone understands this.
Yes, sir.
Now, there is a difference between electric field lines and magnetic field lines. What is the difference between electric field lines and magnetic field lines?
Electric field lines are open and magnetic field lines are closed.
Electric field lines are open curves, but magnetic field lines are closed curves. Do we understand this, or this is going above our head? Saying bye bye.
Understood, sir.
Electric field lines are open curves. What do you mean by open curves? What do you mean by open curves?
Like the end point and starting point never meets.
Electric field lines are in open curves. They start from a positive charge and end on a negative charge, but magnetic field lines, they do not have a starting point or an end point. Outside the magnet, they are going from north to south. Inside the magnet, they are coming from outside the magnet, they are going from north to south, and inside the magnet, they are going from south to north. Do we understand this?
Yes.
A single pole cannot exist, so you cannot have a single north pole or a single south pole. Do we understand this?
Yes, sir.
Have you noted this down?
1 minute.
I'll give you time to note it down. Then these are the properties of the magnetic field lines. Number one, they do not touch, cross, intersect each other, same as electric field lines. The only difference is they are in closed loops, whereas electric field lines are in open loops. The tangent at any point will give you the direction of magnetic field. The more number of magnetic field lines, that means the stronger the magnetic field. Then we had said repulsion and attraction. Longitudinally, they repel, and latitudinally, they attract. Do we remember that? You don't have to remember this. We can understand attraction and repulsion by the contraction and the extension of the magnetic field lines. We have written that in the electric field lines wala chapter. Yes or no?
Yes, sir.
We take it down from here. Do it fast. Now we are going to come across these two terms, magnetic flux and magnetic field, similar to the terms that we have seen in the electrostatic, electric flux and electric field. Electric flux was the total number of electric field lines passing normally to an area. Yes or no? It was a scalar quantity. Do we remember this? First, listen to me, then I'll give you time to write. Don't worry. Magnetic flux was the total number of field lines passing through a particular section. Yes or no?
Yes, sir.
It was a it was a scalar quantity. It could have been positive or negative. Do you remember this? Outgoing flux was positive, incoming flux was negative. Do you remember this?
Yes, sir.
The SI unit of magnetic flux is Weber. CGS unit is maximal. 1 Weber is 10⁸ maximal. Remember this. Then what is magnetic field or magnetic field strength? It is the number of field lines passing. Number of field lines passing what?
Per unit cross section area.
Per unit area. Per unit area. Do we understand this?
Yes, sir.
Magnetic field is the number of field lines passing per unit area. You can determine it like this, or you can call this magnetic field as the force experience per unit pole strength. If I put a isolated north pole in a magnetic field, if this is a north pole, let us say, I mean, this is a fictitious thing. This north pole has a magnetic pole strength of m naught. It will experience a force F vector like this. Then the magnetic field strength will be given by F divided by m naught. Do we understand this?
Yes, sir.
What type of quantity is magnetic field strength or magnetic field?
Vector.
It is a vector quantity. The SI unit becomes Weber per meter square. Do we understand this?
Yes, sir.
You can write it as in different ways, and remember to remember these different ways. Weber per meter square can also be called as 1 Tesla. You will remember Tesla. You might now know Tesla because it is a very famous company now. Tesla. Do you remember Tesla?
Yes, sir.
1 Tesla is 10 raised to the power 4 Gauss. Tesla is the SI unit and Gauss is the CGS unit. Gauss is the CGS unit. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Now let us move ahead. We'll just understand these terms because you just need to remember these terms. There's no way of understanding them. You just have to remember these terms, what am I going to say. Now, whenever you are going to put a magnetic substance in a magnetic field, what will happen to that magnetic substance in a magnetic field?
It experiences magnetic force.
And how will it experience I've just put a magnetic substance in a magnetic field. It will experience magnetic force. Why will it experience magnetic force? Or if I have a medium in which magnetic fields are present, the ability of that medium to allow magnetic field inside it is known as magnetic permeability, or the strength, the degree to which a substance can get magnetized in a magnetic field is known as its permeability. And this magnetic permeability mu is same as whatever we have learned in the chapter on electrostatics. What is it similar to?
Permittivity epsilon naught.
Permittivity not epsilon naught, permittivity epsilon. Permittivity epsilon naught was the permittivity of free space. Here the permeability of free space is known as mu naught. Relative permeability is mu r. There it was known as epsilon r. We also call it by dielectric constant. Do we understand this?
Yes, sir.
Are you able to relate this? Yes or no? Relative permittivity will be the magnetic field in the medium divided by magnetic field in vacuum. Do we understand this?
Yes, sir.
Is it same or is it different? Same or different?
Same.
2 minutes to write the same. Well then, there are other terms that we are going to do here. Again, there is no point of understanding them. You will not be able to understand them. If these terms come, they will come as straight away definition, and you just have to remember the relation, and if you can remember them, you can just put them. Otherwise, these questions are gone, as simple as that. Now, the second thing that we are going to do is intensity of magnetizing field. Now, remember, placing a body in an electric field is not as common question material as placing a magnetic body or a magnetic body in a magnetic field. Whenever you place a magnetic body in a magnetic field, what happens to that body? It gets magnetized, yes or no?
Yes, sir.
The value of the magnetic field in which the body is kept is known as the intensity of the magnetizing field. Do we understand this? So this is the field in which the body is kept. Do we understand this?
Yes, sir.
So the intensity of that field, how much is the strength of that field, is known as the intensity of the magnetizing field, and this is the definition. It is denoted by the letter H. H, 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 H. H, 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 H. And H is B by mu, where mu is the permeability of the medium, and these are the SI units, and the CGS unit of this is Orsted. Remember that. Okay. Remember these terms. The only way to remember this term is write all these terms on a sheet of paper and put that paper on your study table and see it every day. Even I don't remember these terms and I also get confused. So don't look for me for support. I just can't help you here. The only thing that I can tell you is that you will have to remember this. Then the next term is intensity of magnetization. Intensity of magnetization tells us how much the body has the body which has kept was magnetized, and this is same as polarization of dielectric. Do we understand this?
Yes, sir.
In polarization of dielectric, we had put a dielectric in an electric field, and because of that electric field, it gets an induced dipole moment. Yes or no?
Yes, sir.
This is the same as induced dipole moment. It is the magnetic strength per unit area or magnetic dipole moment induced per unit volume. Do we understand this?
Yes, sir.
Remember all these units, because in the examination hall it will become very difficult for you to derive these units. If you don't remember them, you will waste a lot of time in deriving these units. The next thing is magnetic susceptibility, XM. You just have to remember this. No way you can understand all these things because they are just definitions. And you will have to remember their definitions, nothing else. Magnetic susceptibility is the ease of magnetizing of a body. How easily the body can be magnetized, XM, and the value of XM is I by H. It is a scalar quantity. You will have to remember this. It has got no units and no dimension. I'll give you 2 minutes to note this down. Well then, remember this relation between all these terms. Just remember these relation. The total magnetic field is the sum of magnetic field in vacuum produced by the magnetizing field and magnetic flux due to the magnetizing of the material. This is same as when you had put an external field E naught. Do you remember this? Then you had a field inside the dielectric and you had the net field. Do we remember this? It's the same thing, but it is done in terms of magnetism. Just remember these relations. Note this down at different points. Keep them and have a look at them whenever you get time. That is the only way to remember these. Then we come to magnetic force between two poles. Now remember, two poles cannot exist in isolation, but just for the theoretical aspect of understanding it, if you have two poles M1 and M2 separated by a distance of r, the force in vacuum is given by F is equal to K. F is equal to K M1 M2 by R square. Does this sound familiar to something that we already know? Do we understand this? F is equal to K M1 M2 by R. The value of this K for the value of this K for vacuum is mu naught by 4 pi, which is equal to 10 raised to the power minus 4 Weber per ampere meter. Now, if you can correlate this thing with the thing that we had done some centuries ago, Q1, Q2, separated by a distance of R, the electrostatic force between these two Fe was K Q1 Q2 by R square. If they were like charges, it was repulsive. If they were unlike charges, it was attractive. Do we remember that?
Yes, sir.
Similarly, you had found out that at any point, if you have a magnetic monopole, the force per unit monopole, if you have a magnetic monopole M here, and you have a magnetic force acting on that monopole as F, the magnetic field at that point will be F divided by M. Does it remind you? Remember, this M is not a mass. This M is a monopole, south pole or a north pole. Do we understand this? Does it remind you of something that we have already done in the previous chapter? Electric field at any point in space was electric force per unit charge, limit charge tending towards zero. Yes or no?
Yes.
If you had a test charge, a very small charge placed here, the electric force was F, the electric field at that point was F by Q naught. So whatever we have done already, this is just a repetition of it. Do we understand this, or this is going above our head? Saying bye-bye.
We got it.
I'll give you 2 minutes to note this down. Okay, then we can write the same thing in a different way. The force on a magnetic monopole F vector will be equal to M into B vector. Do we understand this? The force on the north pole will be in the same direction as that of the magnetic field, but the force on the south pole will be in the opposite direction. Do we understand this?
Yes, sir.
This is similar to saying force on a positive charge will be in the same direction. Force on a negative charge will be in the opposite direction. Do we understand this?
Yes, sir.
Everyone understands this? If I have a positive charge, the force on the positive charge will be in the same direction as that of your magnetic field, but force on the negative charge will be in the opposite direction of your magnetic field. The magnetic field is going like this. Force on the positive charge, and also remember that this force F vector can be written as Q multiplied by E vector. Yes or no?
Yes, sir.
Everything is similar. So this is the last revision of electric field that we are doing. Do it cautiously. Then let's move, sir. In this sheet, we are going to see the electric field and the magnetic field due to a monopole and a point charge. I hope you understand what I'm writing here. Do we understand this? Yes or no?
Yes, sir.
Everyone understands this? Electric field E will be 1 by 4 pi epsilon naught Q by R square. Do we understand this? Electric field in the vector form can be written as 1 by 4 pi epsilon naught Q by R cube multiplied by R vector. Do we remember this, everyone?
Yes, sir.
If the pole is the north pole, it will be going away. If the pole is the south pole, it will be coming towards. If the charge is a positive charge, it will be going away. If the charge is negative charge, it will be coming towards. Do we understand this? Yes or no? No, yes.
Understood, sir.
I'll give you 2 minutes to note it down. Then we have the formula for magnetic field due to a dipole. Magnetic field due to a dipole at any axial position The formula of magnetic field is given by this one, mu naught by 4 pi 2 mr upon r square minus l square the whole square, where m is the magnetic dipole moment. If this distance r from the center of the dipole is very large, the shortcut formula becomes like this. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
Just a minute, I'll give you time to note it down. Now, this is the axial position. Then we have an equatorial position, which is the perpendicular bisector. Do we understand this?
Yes, sir.
The formula for this perpendicular bisector would be like this. The formula for this perpendicular bisector would be like this. Both the formulae are given together so that you can remember them, and then I'll give you a table as well. Then I will give you a table as well so that you can understand both these formulas together. What we have to note here is the direction of magnetic field. The direction of magnetic field is same in this case as the direction of magnetic dipole moment. You can see, my dear friends, the magnetic dipole moment is like this. Do we see this? Please listen to me, then only you will write the magnetic dipole moment. You can see is in this direction. Do we understand this? And the magnetic field B1 will be powerful. The magnetic field, the net magnetic field will also be in the same direction. So the direction of magnetic field B net is same as the direction of magnetic dipole moment. Are you able to understand this?
Yes, sir.
But here you can see the magnetic dipole moment is like this. The magnetic dipole moment is like this, but the magnetic field is in the opposite direction. So remember this, magnetic field B is opposite to M. Will you remember this?
Yes, sir.
These are the two formulae. Now I'll give you 2 minutes to note them down. And this is the table giving you the comparison between electric dipole and magnetic dipole. I think we have already discussed this, yes or no?
Yes, sir.
We know this, or you want to note it down? This is in the tabular form. You want, you can note it down. You want to note it down?
No, sir.
Okay. Now, we had seen the electric field. We have seen the magnetic field due to a dipole. The magnetic field due to a dipole is on the right hand side. The electric field due to a dipole is on the left hand side. Do we see this?
Yes, sir.
As you can see here, I hope you can see this is smaller because I cannot just make it more large. Magnetic field is like this, electric field is like this. Here we have taken the distance to be very large compared to the pole dipole length. Do we understand this?
Yes, sir.
This is the electric field in the axial direction. This is the electric field in the radial or equatorial direction. At any general point, if I take any general point, do you see this general point? Yes or no?
Yes, sir.
The electric field will be given by this formula. If the angle is different, you can just put, if you put angle as 0, you will get electric field at the axial point. If you get angle at 90 degrees, you will get electric field at the equatorial points. Do we understand this?
Yes, sir.
The last point is electric potential. You know, there is a magnetic potential that is defined for a bar magnet, but that is not in your course. Therefore, the magnetic potential wale formulae are not here. But there is electric potential which is in your course, and this creates an electric potential at different points. These are the formula given in the next slide that I will show you. I will show you the bifurcations. You can note this thing down. On the right hand side, you have magnetic field. On the left hand side, you have electric field. If you don't want to write them side by side, you can just write down the formula for electric field at general points and other points. Do you understand what I'm saying?
Yes, sir.
I'll give you 2 minutes. Do it fast. Then this is the formula of electric potential due to a dipole at any axial point, at any equatorial point. I told you equatorial point it is 0. At any general point, if you put angle as 0, you will get axial point 0 or 180 degree. If you put angle at 90 degrees, you will get equatorial point. Do you understand this?
Yes,
Note
sir.
down this formula because you might not have this formula with you. And this is the next question, sir. if the magnitude of intensity of electric field at a point X on the axial line and a distance Y on the equatorial line for given dipole are equal, what is the ratio of X is to Y? This question could be made for an electric dipole, it could be made for a bar magnet. The question remains same. I hope you understand this. Yes or no?
Yes, sir. Sir, it's
Okay.
1:2, sir.
The answer is
1:2.
take deep breaths. Deep breaths. Deep breaths you take. Close your eyes. Think about it. Open your eyes. Look at the question and then give me the answer. Do not rush on to answers. Whenever you rush on to your answers are definitely not correct. Take a deep breath. And that is a mistake probably you have done in your physics papers. You just rush on to the answers. The questions were so simple. Deep breaths. Deep breaths. So, electric field at a distance of x on the axial line, I have given you the formula. Electric field at a distance of y on the equatorial line, I have also given you the formula. You cannot solve it from there. It's a shame for you. It's a shame for me. Electric field on the axial line is k into 2p by distance x cubed. That must be equal to k into p by y cubed. I hope you can solve it from here. Once you get this, the answer will be option D. 2 raised to the power 2 by 3. 2 raised to the power 1 by 3. Cube root of 2. That is the answer. Not 1 is to 2. 2 is to 1. I hope we have learned a lesson. Have we learned a lesson here? Yes or no?
Yes, sir.
Thank God. You must, I'll request you, whenever you have your bath, after your bath, go back and pray to God for 5 minutes every day. 3 charges, plus 2q, minus q, and minus q are placed in corners ABC of an equilateral triangle of side A as shown in the adjoining figure. And the dipole moment of this combination is, praying to God is always good, and especially good now, the examination time. This one. Yes?
Option C, sir.
Option C, sir. And that is the correct answer, sir. You see, praying to God helps. Praying to God always helps. It's a good thing that the praying to God helps. So from now onwards, after your bath in the morning, this is one dipole, minus q plus q like this. This is the other dipole, minus q plus q like this. The dipole moment of this gentleman is P. The dipole moment of this gentleman is P. Do we understand this?
Yes, sir.
These two dipoles are inclined at an angle of 60 degrees. P squared plus 2 times P1, P2 cos theta. Yes or no?
Yes, sir.
P square plus P square plus 2 times P square cos of 60 degrees. And we land up here. Root A root 3. Do we understand this? Yes or no? No, yes.
Understood, sir.
So happy. Good. Then comes this one. See, praying to God helps. A short bar magnet, which is north pole facing north, forms a neutral point. What do you mean by neutral point? The point where the magnetic field is 0. I hope you understand this. Yes or no? The magnet is rotated by 90 degrees in the horizontal plane. What is the net magnetic induction at the point P? The horizontal component of Earth's magnetic field is H. Now, what is the horizontal component of magnetic field? You don't know the horizontal component of magnetic field. So I will let go this question, and probably I'll do this question when this magnetic field is done. So I will let go this question. I did not see that it had magnetic horizontal component of magnetics. I'll do this question later on. I will replace this question with this one. A bar magnet of magnetic moment, this is placed in a uniform magnetic field. If each pole of the magnet experiences the force of this one, what is the length of the magnet, my dear friends? Answers. So how are you supposed to do this? Dipole magnetic dipole moment is given, and the force on the one of the poles of the bar magnet is given. Force is m into b, my dear friends, m into b. From here you will get the value of small m. Or you can write it as m by l into b. This is the simplest calculation. You have to multiply and divide, but yeah, it's a problem. You have to multiply force with length. So this is one multiplication. Then you have to divide it by b. It's a very long thing to do. You have to multiply and divide. Once you multiply and divide, you should be getting the correct answer. What is the answer that you are getting? By multiplying 0.5 or 0.1? In the sheet I have 0.1. Is it 0.5 or 0.1? If you cannot multiply and divide, I don't know what you can do.
Sir, it is m by L or m by 12.
Take deep breaths. Deep breaths. Deep breaths. Deep breaths. Deep breaths. Close your eyes. Think about it. 2L or L. That was the length of the magnet. Deep breaths. Open your eyes. And then you will see that the answer is 0.1. Yes or no? You take deep breaths. The problem with you guys is you jump onto the question. Jump onto the solution. 2L. I have to find the value of L. Hey, what was 2L? Why it was given as 2L? So that the distance from the center becomes L. That is why it was given as 2L. 2L was the magnetic length of the magnet, my dear friends. Magnetic length of the magnet, my dear friends. Small things, if you make mistakes like this, you are ruined. Forget about IIT. Forget about NIT. You will not get into the bloody private engineering college of your city if you make mistakes like this. Not acceptable. Not acceptable after the sort of effort that we are putting, the sort of fee that you would have been paying. It's not justified. It's just not justified. That is why I tell you, before writing, understand what you are writing. You bloody write, but you don't understand what you are writing. Whenever you hear L, okay, it has to be the length. 2L is the length here, bhai. Cannot afford mistakes like this. Because if you do stupidity like this, that is the reason your percentiles are so revolutionary. Again, praying to God would help. Definitely. Two identical magnet dipoles of magnetic moment 0.1 ampere, 1 ampere per meter square each are placed at a separation of 2 meter with their axes perpendicular to each other. This is how questions are framed. The resultant magnetic field at a point midway between the dipoles is. Do not be in a haste to give an answer. Do not be in a haste. Questions are simple, my dear friends. Questions are simple. Out of the 30 questions, you are only supposed to attempt 25. Out of that 25, 20 questions will be bloody simple. And if you get 18 correct out of those 20, you are in the top 95 percentile just because of physics only. Forget about chemistry and maths. You can do 18 out of that 25 correctly. In the top 90-95 percentile of the students that are appearing, and you get your NIT at least. Chemistry and maths will just get you to a better NIT. Patiently do it. Patiently. Questions are pretty damn simple. You would have realized it. But if you are making mistakes, which are absolutely rubbish, cannot be justified. There has to be a reason to justify it. The mistake that you are making is not justifiable from any stretch of imagination. Take your time, get me the correct answer. So how are we supposed to do this? If I make one of the dipoles like this, M, the other dipole would be like this. Do we understand this?
Yes.
Their axes are perpendicular. And I have to find the electric field at this point, which is the center of this. Yes or no?
Yes,
The
sir.
distance of this point from both the dipoles will be 1 meter. Yes or no?
Yes, sir.
The electric field due to this dipole, the dipole moment is like this, will be going in this direction. Yes or no?
Yes, sir.
The electric field due to this dipole, which is like this, would be going in this direction. Yes or no?
Yes, sir.
One field will be axial, the other field would be radial. Yes, the other field is equatorial. What is the axial field? E1. Let me call this as E1. How much is the axial field? You can write B1, not E1, B1. B1 will be equal to mu naught by 4 pi. This is axial field. So 2p divided by 1 cube. Yes or no? This is the equatorial field B2 in the equatorial direction. Mu naught by 4 pi divided by p by r cube. Both these fields are in mutually perpendicular direction. So B net will be equal to root over B1 square plus B2 square. If I write one field as B, the other field is 2B. A root 5 wala term, 1 square plus 2 square. Root 5 wala term will come. The only option which has the root 5 wala term is this one. The answer is option B. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Note this down. If you have any doubt, please ask. Understood this?
Yes, sir.
Noted this down?
One
Let me
minute.
know once you are done. Then we have this question due to a small bar magnet. Intensity at a distance x in the end means actual position. In the end position is 9 Gauss. What will be the intensity at a distance of x by 2 on the broad side? Broad side means equatorial, end side means axial. Broad side means equatorial, end side means axial. Broad side means equatorial, end sides mean axial. You have 2 minutes to give me the answer for this one. And the answer is definitely 36 Gauss. Magnetic field on the axial point or end point is, let me write it as K so that we can do it, K into 2m by r cube. Magnetic field on the broadside point, it is at a distance of x by 2. So K into m divided by r by 2 ka cube. Do we understand this?
Yes, sir.
From there, once you divide, this field is given as 9 Gauss. You have to find out the value of this field. You just have to multiply, divide, and you will end up with this answer. Do we understand this?
Understood, sir.
Everyone understands this?
Yes, sir.
Great. Remember, the paper that you are going to see or face is going to be a pretty straightforward, simple one. And you have to keep it that way. It is a simple paper. It's a simple paper and you have to keep it that way. Tough questions are not going to come. Tough questions are not going to come. Remember that. You just have to remember simple things, and this is one of the things that you have to remember. Whether it's an electric dipole or whether it's a magnetic dipole. I've seen questions come on this. A point charge and a dipole. Whether you call it a point charge or a monopole or electric dipole or electric monopole, a magnetic dipole, the concept is same. Potential due to a point charge at any point is proportional to 1 by r. Yes or no? But
Yes.
for a dipole, it is proportional to 1 by r squared. Remember this. Electric field due to a point charge or a monopole is proportional to 1 by r square. But if it is a dipole, it is proportional to r cube, 1 by r cube. Remember this. Force between two point charges is proportional to 1 by r square. Force between one dipole and point charge is r cube, 1 by r cube. Force between two dipoles is r raised to the power of 4. Don't forget this. I've seen some straightforward questions coming on this. Very simple. But if you don't know this, you are done. Note it down. Once you're done, let me know. Then this is the next question, sir. A point charge placed at any point on the axis of an electric dipole at some large distance experience a force F. The force acting on the point charge when its distance from the dipole is doubled is what will happen to the force if the distance of the point charge from the dipole is doubled? And the answer is
F by 8.
F by 8. It is proportional to 1 by r cube. The distance is doubled, so the force becomes 2r ka whole cube. 8r cube, it becomes 1 by 8 times. Do we understand this, or this has gone above our heads? Saying bye bye.
Understood, sir.
These questions are more likely to come. Looking at the present trend of the questions. Force between two identical bar magnets whose center are r meter apart is 4.8 Newton when their axes are in the same line. If the distance is increased to 2 r meters, what is the force between them? I'll give you a minute to know to do this. Option how much?
B, 0.3, sir.
0.3 newtons. Remember, the force between two dipoles is inversely proportional to 1 by r raised to the power of 4. Do you understand this?
Yes, sir.
So when the distance between them is doubled, the force becomes 1 by 16 times. We understand this.
Yes, sir.
And therefore, the answer is this one. Everyone gets this?
Yes, sir.
Then I shall give you this question, and this question is given for a reason, whether you have understood something or not. I'm not very confident whether you would have understood what is there to be done in this question. An electric dipole is placed at the origin O and is directed along x-axis. At a point P far away from the dipole, the electric field is parallel to y-axis. OP makes an angle theta with the x-axis, then what is the angle theta equal to? Now, since I don't have time, I will give you the diagram. Remember, the diagram is not a part of this question, but I'm going to give you so that you can give me the answer for this question quickly. So you have 2 minutes to show me your talents. This is the diagram of the question. Your time starts now. Well done. The answer is root 2. Now, what I wanted to make you understand is how you relate this diagram with this. This angle was phi. Do we remember this if you have drawn the diagram correctly?
Yes.
This was the dipole axis and the angle with the dipole axis was theta, and you must remember tan of phi was tan of theta by 2. Do we remember this?
Yes, sir.
Now, if I say the angle that this field B net makes with the x-axis, the angle that this field makes with the x-axis, that is what I wanted to tell you, is theta plus alpha. Do we understand this?
Yes, sir.
Now this theta plus alpha here is given as 90 degrees. Do we understand this?
Yes, sir.
So your alpha, oh sorry, theta plus not alpha, I am writing it as alpha. This is theta plus phi. Theta plus phi. Do we understand this?
Yes, sir.
So from here you can find out theta will be equal to 90 minus phi. So tan theta will be equal to cot theta by 2. Yes or no?
Yes.
Do we understand this?
Yes, sir.
Or I have done it wrongly? Theta, I think I have done it. Phi is tan theta by 2. So by 2 will come here. See, I always make mistakes with ratios and proportions. So from there you will get tan square theta as 2 and tan theta as root 2. Do we understand this?
Yes, sir.
This is what you need to understand in question of this nature. If this question comes, well, you never know. I feel that these questions can come, and I only do those selective questions that I think are most likely to come. And the point that you have to note, and I keep on insisting on those points, are you must remember what we have done. Nothing can come outside what we have done. If even a single question comes, I am held responsible, but there will not be anything that will come outside of what I have taken in the class. If I have not taken a topic, that is a different issue altogether. But again, there are 5 questions which will be coming as options, and topics that probably we would have left would be coming in those 5 questions. So still, if there is a topic that is left, a smaller one or which it is left, that will be coming as an optional question, trust me on that. I have full faith on that side. Having said that, we are done with this. We are not done with dipole. There are still 1 or 2 things left in the dipole. We might not be doing those things now. We might be doing it because we will again have to encounter this dipole after some time. So probably we will be doing those things there. Let's see how it turns out. In any case, magnetic field is started, and I intend to finish it by the end of this week. Probably by next week we must be done with electromagnetism. Still entire magnetic field is left, EMI is left, EM waves is left. One question always comes from there. AC is left, one question comes from there. Maybe it will take 7 to 8 days to wind up your electromagnetism. Once we are done with electromagnetism, we will move swiftly into modern physics, and we'll try to cover modern physics in detail, because 3 or 4 questions are going to come from modern physics. So whatever we are doing in the span of, even if you start from today to the end of your course, we will be covering around 10 to 12 questions. So even if you have not understood anything up till now, from this class to the end of the course, we were still having 10 to 12 questions in our hand. And 10 to 12 question correct means, again, you have cleared JEE, apart from other things. So take care. I'll see you in the next class. Have a nice day. Bye-bye.